Every time you flip a light switch, electricity appears instantly. It doesn't matter whether it's the middle of the afternoon or 2 o'clock in the morning. Millions of people are constantly turning devices on and off, yet the lights stay on. So here's the question. How does an entire continent keep electricity flowing every second of every day? The answer is surprisingly strange. Engineers often describe the power grid as one giant synchronized machine. That's not literally true for all of North America. There are several major interconnected grids, but within each grid, thousands of generators must operate together as though they're parts of the same machine. Understanding how that works is the key to understanding the modern power grid. Before we can understand the grid, we need to understand where electricity comes from. Nuclear plants, hydroelectric dams, wind farms, and natural gas plants all look completely different. But despite those differences, most of them rely on the same basic idea. Their job is to spin a machine called a generator. Inside a generator, magnets rotate past coils of wire. As the magnetic field moves, it pushes electrons through the wire. That movement becomes electricity. It's a remarkably simple idea, but it powers much of modern civilization. This principle was discovered by Michael Faraday in the early 1800s. Faraday spent years experimenting in the basement laboratory of the Royal Institution in London. The Royal Institution still hosts scientific lectures today. During one experiment, he discovered that moving magnetic fields can create electricity, a discovery that eventually made modern power plants possible. At this point, a natural question appears. If generators are pushing electrons through wires, why don't the electrons simply flow in one direction? The answer comes from the spinning magnet itself. As the magnet rotates, its magnetic field continually changes orientation. That causes the electrical current to repeatedly reverse direction. This back-and-forth motion is called alternating current, or AC. In North America, the current reverses direction 60 times every second. Engineers call this 60 Hertz. That number might sound like a minor technical detail, but by the end of this video, you'll see why it functions as the heartbeat of the grid. You might be wondering something. If current is constantly reversing direction, doesn't that cause a problem with something as simple as lighting a bulb? It turns out it doesn't. The reversing current does cause the bulb to pulse, technically flickering 60 times every second, but we never notice it. The human eye cannot perceive flickering that fast, and the bulb's filament doesn't instantly go cold between pulses. It stays hot, creating a brief physical lag. By the time the filament begins to cool, the current has already reversed again. The result is steady, continuous light, even though the electricity driving it never stops reversing direction. There's a common misconception worth clearing up. Most people imagine that a power station pumps electrons down a wire and into your TV, where they get used up. But that's not what happens. Your wire is already completely packed full of electrons, like a pipe that's already full of water. The power station doesn't deliver electrons, it delivers energy. Think of a chainsaw. Direct current is like the chain moving continuously in one direction. Alternating current is like a traditional handsaw. You push forward, pull back, push forward, pull back. In an AC circuit, electrons don't travel anywhere. They vibrate back and forth 60 times a second. As they shake, they collide with atoms in the wire. That atomic friction is the heat in your toaster, the light in your bulb, and the magnetic field powering your microwave. But there's a catch. Everything we've described works perfectly for heating, lighting, and running motors. But batteries are different. A battery stores energy through a chemical reaction, and that reaction only works in one direction. Electrons must flow in, consistently, steadily, to build up the stored charge. Alternating current, by definition, keeps changing direction, so it can't charge a battery directly. Your phone charger solves this by converting AC from the wall into DC before it reaches the battery. That conversion happens inside the small block you plug in. It's called a rectifier. Strip away the plastic and that's essentially what's inside. A circuit that lets electrons flow in only one direction, turning the back and forth of AC into the steady push that a battery needs. At this point, you might be wondering something. If generators naturally produce AC, why was there ever a debate about using AC versus DC? Why didn't everyone simply use alternating current from the beginning? The answer takes us back to one of the most famous engineering rivalries in history. In the late 1800s, Thomas Edison had already built electrical systems based on direct current, or DC. DC was simple, familiar, and already powering parts of New York City. Meanwhile, Nikola Tesla believed alternating current was better suited for large electrical networks. Their disagreement became known as the War of Currents. The debate wasn't really about light bulbs, it was about distance. Electricity loses energy as it travels through wires. The farther it travels, the more energy is wasted as heat. Engineers needed a practical way to move electricity across entire cities and eventually across entire regions. Tesla's solution depended on a device called a transformer. Transformers can dramatically increase voltage before electricity begins its journey. Higher voltage means less current is needed to deliver the same amount of power. Less current means less wasted energy. This made large-scale electrical grids practical. One of the most famous demonstrations came from Niagara Falls. Engineers used AC power to transmit electricity from the falls to Buffalo, New York. It was one of the first major demonstrations that electricity could be generated in one place and used far away. The success of that project helped convince the world that AC was the future. Now we know how electricity is generated. We know how it travels long distances. But we're still missing the most important piece of the puzzle. If thousands of generators are connected together, why don't they fight each other? Why doesn't one generator try to speed up while another slows down? Imagine thousands of drummers playing together in a giant stadium. If every drummer keeps the same rhythm, the music sounds perfect. But if enough drummers drift apart, the performance becomes chaotic. The power grid faces the same challenge. Every generator must stay synchronized with every other generator. Within each major grid, generators continuously adjust themselves to stay synchronized. Together, they maintain a shared frequency of 60 Hz. Engineers constantly monitor that frequency because it reveals the health of the entire system. In many ways, 60 Hz functions like the heartbeat of the grid. But what causes the heartbeat to change? The answer is supply and demand. Electricity is surprisingly difficult to store at large scales. That means power plants must generate almost exactly as much electricity as consumers are using. Every air conditioner, factory, data center, and phone charger affects that balance. During the Texas power crisis of 2021, operators closely watched grid frequency as power plants went offline and demand surged. If frequency falls too far, generators can automatically disconnect themselves to prevent damage. That can make an already difficult situation even worse. Maintaining frequency is one of the grid's most important jobs. The challenge becomes even greater because the grid is interconnected. In 2003, a failure in Ohio triggered a cascading blackout that affected roughly 50 million people across parts of the United States and Canada. A problem that began locally spread through a much larger system. That's one of the trade-offs of building one of the largest synchronized machines in human history. The next time you flip a light switch, remember what's happening behind the scenes. Thousands of generators are spinning in synchronization. Electricity is being produced at almost exactly the same moment it's being consumed. Millions of miles of wire connect cities, power plants, and industries together. Most people think they're connected to a nearby power plant. In reality, they're participating in one of the largest synchronized machines humanity has ever built, and its heartbeat is 60 Hz.